Welcome to a refresher lesson for exponential and logarithmic functions graphing. This video corresponds to the examples on a worksheet packet that can be found at my Teachers Pay Teachers store. In this video, I will explain the skills and steps necessary to complete all of the examples on the worksheet. Please feel free to skip around to engage in the concepts with which you would like some help. So if we are talking about graphing of functions, we're going to start by talking about the parent functions, which means we're talking about the simplest form of that type of function or that family of functions. So in the exponential family, the simplest form of the exponential is f of x equals some base to the x power. We need that base b to be something that is positive, and it cannot equal 1. Okay, so as an example, we are going to take a look at what happens if our b value is something bigger than 1. So let's say 2, and let's take a look at what happens if we graph the function f of x equals 2 to the x. Now, if we just go with some straight plug and chug, we can put in some different values of x and record what the resulting y values would be. So with our negative exponents here, we can see that we get fractions for our results. Then when we use 0, we're going to get 1, and that's true regardless of what our base is. And then when we're using our positive exponents, we are getting those larger results. And as the x gets larger, the results will get larger. Okay, so when we plot these points, we get a curve that looks something like this. Our negative values for x down here are getting smaller and smaller results, whereas our positive values of x up here are giving us bigger and bigger results. And so overall, the trend of the curve is that we have an increasing curve, which is sometimes referred to as exponential growth. And exponential growth is characterized by the fact that instead of adding a constant value every time, as we did in linear, we are multiplying by a constant value each time. And that constant value is the 2. So we are multiplying the result by a 2 to get the next result, and that gives us this curve, which is growing exponentially. Now, it is also possible, remember we said we wanted b to be greater than 0. And in this case, we're looking at an example where b was greater than 1. We can also have b be something that's in between 0 and 1. We cannot have 1. We've already talked about that. But we can have something between 0 and 1. And so if we look at an example of using 1/2 as our b value, and again, go through the process of picking some x's and looking at the resulting y's. Now, when we look at our negative values, we get the larger results from those because the negative is going to actually take the reciprocal of this 1/2 and raise it to the power. Again, we have our 0, 1. And then as we put in these larger numbers, positive numbers for x, we're getting the fraction results for y. And so what that means is we are looking at a decreasing graph in this case. So having a b value that's something between 0 and 1 means that we're going to have a decreasing graph, which is often referred to as exponential decay, where we're starting with bigger numbers to the left and getting smaller and smaller and smaller as we go with bigger x values to the right. Now, regardless of what our b value is, there are some characteristics that are true about all exponential parent functions, no matter what the b is. So the first is we have a horizontal asymptote at y equals 0, which is our x-axis. And you can see that in both of these cases, our x-axis here and our x-axis here, both of those are kind of a boundary that our curve is getting closer and closer and closer to, but never actually crossing, because you can never actually get 0 as an answer if you take b to some power. Okay, so that is true regardless. When you look at domain and range, for domain, you can use any value of x. So our domain is all real numbers. But for the range, because our graph stays above our x-axis, we only get positive results. So our range is only going to be y values that are bigger than 0. We always have a y-intercept at 0, 1. So you can see that here and here, because no matter what the base is, if we take it to the 0 power, we will get 1 as a result. So in the parent function, we always have that 0.01. And there will be no x-intercepts because, again, the x-axis is our asymptote. We never get to the asymptote. We never actually cross it. It is not possible to get 0 as an answer for our y value, and so there are no x-intercepts with exponential parent functions. Now, because we can have different values for b's, there are a few tricks that you can keep in mind when you're asked to graph an exponential parent function. So for example, if I ask you to graph f of x equals 3 to the x, some of the easiest points to start with are going to be 0, 1, obviously, because as we just said, that is a point all the time on a parent function. And then the point 1b, whatever that b would be, in this case, that's 3. And then -1 and the reciprocal of b. And then from there, you can add some extra points in as you need to. So here we've got the point 0, 1, right there. We've got the point -1, 1/3, and we've got the point 1, 3. So we're starting out with those 3. And then for additional points, I would usually say go in the direction that is where the y values are increasing. So in this case, that would be going further to the right, because those are going to be a little bit easier to actually plot. And so I went with an additional point of putting in 2 for x, getting 9 for y, and I plotted that point. Okay. And then once you've plotted 3, 4 points to get a good idea of what that curve is going to look like, and again, keeping in mind that we have our y-axis, x-axis, y equals 0, x-axis as a horizontal asymptote, then we're going to put in our curve. So we fit a smooth curve among those points, keeping it above the x-axis, and that will be our graph for an exponential parent function. Now, that's our starting place with exponentials. We've talked in a previous lesson about how we can make other functions within the same family by using transformations. And this is for any family of functions. So whether it's exponential, logarithmic, rational, whatever it is, you can always use these transformations as a way to create other functions within the same family. Now, I'm not going to go into great detail with this. If you want more detail, I recommend you go back to the rational exponents and radicals lesson on graphing. But if this is something new or you need a quick refresher, I do recommend that you pause the video for a moment and take a good look at these transformations so that they make sense as we use them in a couple of examples. All right, so if we're going to graph a more complex exponential function, like f of x equals 2 times 3 to the x minus 1 minus 4. The first step I would recommend is to identify your b value. So in this case, our b is 3. And then think about what is the parent function going to look like for 3 to the x. So just for a second, I'm going to think about f of x equals 3 to the x power. This would be the parent function. And we just talked about that. So again, we would have 0, 1 as a point. Then we would have 1, 3 as a point, -1, 1/3 as a point, and then I would probably go 2, 9 as a point. So that gives me an idea of what the parent function curve would look like. And I'm just going to kind of sketch it in here for a second with a dotted line just to give me an idea of what I'm starting with. Then I'm going to identify all of those values, the A, the B, the H, the K, all of those values that could change our graph in some way. So I'm going to make a list, A, B, H, and K. I'm going to identify the value and if there's any kind of transformation that would be done. So I have an A value of 2. I have a B value of 1 because that would be something being multiplied to the x, and we don't have anything there other than 1. H is going to be 1 because remember the minus is part of the structure. So it's +1 for the H that's here in the exponent with x. And then our K is -4. Now, what effect are those numbers going to have on our graph? Well, the A of 2 means I'm going to have a vertical stretch by a factor of 2, which means that every y is going to get multiplied by 2 from my parent function, every y coordinate. A b value of 1 really doesn't change anything, so I don't have to worry about it. An h value of 1 means we're going to be moving the graph 1 unit to the right. And a k value of -4 means we will move the graph 4 units left. Okay, so I recommend that you start with A and B values, whatever transformations that they suggest is what you would want to think about first. So I'm going to take every y coordinate that I have in my parent function and multiply it by 2. So if I start with this point, I get 0, 1, multiply the y value by 2, and I get 0, 2. Here I've got 1, 3. So multiplying by 2 is going to give me 1, 6. Then I have 2, 9. Multiplying the y coordinate by 2 will give me 2, 18, which is right there. And then if I go in the negative direction, -1 gave me 1/3. Multiplying by 2 is going to give me 2/3. Okay, so that's the effect of our A value of 2. Then I would recommend that you take a look at the H and the K next. And those are going to take this shape, whatever you have now, and move it around. So we're going to move every point now 1 unit to the right and 1 unit to the right and 4 units down. Sorry about that. This one should have been down, not left, because K affects our up and down vertical shift. So every point is going to get moved 1 unit to the right and 4 units down. Okay, so if I start here, 1 to the right and 4 down is going to put me right there. Then I'll go to my next point here, 1 to the right, 4 down, puts me right there. Then I'm going to go to this next point, our y-intercept, 1 to the right, 4 down. And finally, our -1 2/3 point is going to go 1 to the right and 4 down. And make sure that you're kind of keeping in mind that it's not on the line. Okay, so 1 to the right, 1, 2, 3, 4 down. It's like right there. Okay. The other thing to also keep in mind is that with exponential functions, our k value always tells us where our horizontal asymptote is going to be. So y equals -4 is our new horizontal asymptote. And that's going to be right here. Because along with all of the points that got moved down 4, so did our horizontal asymptote. All right, so now you've got the points, and now you can fit your curve through those points as best you can, curving it into the asymptote as well as you can. And that is what your final graph would look like for f of x. Okay. All right, let's think about logarithmic parent functions now. So again, the most simple form of a logarithmic function is f of x equals log base b of x. Same criteria still hold as with the exponential. B has to be greater than 0. B cannot be equal to 1. So all of that is still true. And we do again get slightly different graphs based on whether b is greater than 1 or if b is something between 0 and 1. So let's think about b greater than 1 first of all. So as an example, we'll take a look at f of x equals log base 2 of x. Now, honestly, I find the easiest way to graph logarithmic functions is to first think about the inverse exponential function. So if b is 2 here, I can think of the exponential function where b is 2 and come up with the xy coordinates for several points of that function. And then using the fact that exponential and logarithmic functions are inverses of each other, that means that whatever coordinate points I have here, I'm simply going to switch those points to get a point on the logarithmic function. And so you can see that all the way down. If I had -2 1/4 for exponential, then on the logarithmic, 1/4 -2 is a point. If I have 1, 2 in my exponential, then 2, 1 is going to be a point on my logarithmic. So I then plot the points from this table that I get from switching all of those coordinates, and I get the logarithmic graph of log base 2 of x. The other thing that you can use to kind of visualize how this should look is to again remember that exponential and logarithmic are inverses of each other. And one of the characteristics of inverse functions is that they have to be a reflection of each other through the y equals x line. So if the green line here that you see is the y equals x line, then you can see that the red curve is what 2 to the x looks like. And then the blue curve is what log base 2 of x looks like. And you can see how they are indeed reflections of each other. Okay. So this is all fitting together with what we know about inverses. Now, if we take a look at when b is something between 0 and 1, we would go through a similar process. First, we're going to consider, for example, if we have log base 1/2 of x, we'll consider what happens if we have 1/2 to the x power. We'll get the coordinates from that equation, and then we'll switch those coordinates to get the points that would be on the logarithmic function. And then we plot those points, and that will give us our graph there. And again, if you want to think about this more visually, we can take a look at 1/2 to the x. So there's our decreasing function that we saw earlier. And then if we take the log of 1/2 x, again, you can see that reflection through the y equals x line. So it makes sense that these are inverses of each other and that we can use that to make graphing the parent logarithm a bit easier. Okay. So characteristics for logarithmic parent functions. You'll notice that most of these characteristics are in line with the kinds of characteristics that we talked about with the exponential, but they're kind of the flip-flop of them. So for example, on exponential, we said the characteristic was that you had a horizontal asymptote at y equals x. Now, because of it being the inverse on the logarithmic parent function, you have a vertical asymptote at x equals 0. So instead of y equals 0, we're now at x equals 0, the y-axis. Similarly, with domain and range, we know that if we're switching the x and y coordinates in the points, then that means we're switching the domain and the range. So now it is the range where we can use any numbers, we can get any result. But for domain, we can only use x values that are greater than 0. There is no y-intercept because, again, that is a vertical asymptote, so we cannot have any y-intercept. And the x-intercept now is the switched point from the y-intercept on the exponential, which is the point 1, 0. So those are characteristics for all parent functions. And again, what you're seeing is just a reflection of the exponential graph through the y equals x line. So again, if you're being asked to graph a logarithmic parent function, I would really say figure out what your base is. So identify your base and then consider what is that in exponential form. Come up with a few key points from the exponential function. Then switch those coordinates to get the logarithmic points that you need. From there, you can plot those points. And then keeping in mind that you have a vertical asymptote now on your y-axis, you will fit in your smooth curve among the points and curving into your vertical asymptote. Now, to do logarithmic graphing with transformations, again, I would really recommend that you start by looking at what your base is. So here we have a base of 2. So I would just kind of off to the side say, all right, so if I did y equals 2 to the x, kind of what points would I be using? So I would be using -1, 1/2. I would be using 0, 1, 1, 2, 2, 4, maybe even going as far as 3, 8 if you needed to. Okay. Then using that to come up with, all right, so the parent function of just log base 2 of x is going to be the switch of those. So I'm going to have 1/2 -1. I'm going to have 1, 0. I'm going to have 2, 1, 4, 2, and 8, 3. Okay, so that gives me a good idea of what I'm starting with for a log base 2 graph. And then just like we did with exponentials, I want to identify those a, b, h, and k values to see what effect they're going to have on my graph. So in this case, a is a -1, b is just 1, h is a 2, k is a 1. So the effect is that -1 for a is going to be a reflection through the x-axis. B being 1 doesn't cause any change. H being 2 means we're going to move 2 units to the right. And K equal to 1 means we're going to move 1 unit up. So again, I would recommend you look at A and B first. And that reflection means that every y coordinate in the parent function becomes the opposite. So here I'm going to have 1/2 +1 now. The 1, 0 doesn't change because there is no opposite of 0. Then I have the 2, 1 is going to become 2, -1. 4, 2 becomes 4, -2. And 8, 3 becomes 8, -3. Okay, so that's where my points would be based on the reflection. And then if we look at the h and the k, we're going to be moving 2 to the right and 1 up. So each of these points goes 2 to the right and 1 up, 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 and then 2 to the right and 1 up. Okay, and now in this case, remember we said K told us where the horizontal asymptote would be in an exponential function. Well, now it's the H that tells us where the vertical asymptote will be in our logarithmic. So the vertical asymptote is going to be at x equals 2. So that's going to be right here. And now we can graph our function using the points and curving it into that asymptote as best we can. Okay, I know that looks a little bit like I crossed it, but just imagine that that's really just hugging in there pretty tightly and not crossing. There we go. All right, so that is how we graph our parent functions for exponential and logarithmic functions and how we can use transformations to graph more complex functions in each of those families. I hope that you found this helpful. If you would like to see other concepts that you need to refresh or review, please check out my Gordon Global Math page on YouTube. Videos covering Algebra 2 and pre-calculus concepts will be added throughout the spring of 2025. Thanks for watching.